We worked out that a system of cold bosons exhibit Goldstone mode, which is responsible for superfluid behavior. And the corresponding Lagrangian at low energy is given by a scalar Lagrangian for a massless Goldstone field theta. And this Goldstone mode corresponds to rolling along the gutter, and that corresponds also to a gauge transformation of the initial field phi, so a global gauge transformation. So when we consider global gauge transformation on theta, that only adds a constant to theta, because theta can be seen as the angle in the bottom of this potential. We see that this Lagrangian is invariant under this global gauge transformation because alpha is just a constant and only derivatives appear. And that's why the Goldstone mode is massless, because if there was a mass term in the Lagrangian, then this transformation will not leave the Lagrangian unchanged, and it will not be global gauge invariant. So we know that because there is a global gauge invariance, there must be another current which is conserved. We already worked out that the time-like component of this current is a particle density up to a minus sign. In that case, J must be the current of particles, again up to a minus sign. The more particles we have, the larger the current, therefore J must be proportional to rho. And the faster the particles move, the larger the current as well. Therefore, it must be proportional to the velocity. And we can work out its expression from the expression of J mu according to Noether. From the action of the gauge transformation on theta, we see that delta S theta is just 1. If the density is constant, it is just equal to n, and therefore we get an expression for the velocity. This result is quite interesting because we are usually told that the phase doesn't matter. But here we see that it is important because its gradient is proportional to the velocity of the particles. We will now see a consequence of this expression when we try to rotate a superfluid. Let's first consider the case of a normal fluid. The fluid is contained in a cylinder with angular velocity omega. In this case, the further we are from the center, the faster the fluid rotates. In particular, the velocity magnitude is proportional to r. Let's now look at the case of a superfluid. The superfluid is described by a scalar field phi. We already saw that the amplitude of the field is the square root of the density, and the phase is just the Goldstone mode. We do not constrain the system to have a constant density. However, by symmetry, because we have the superfluid in a cylinder, we see that the density can only be a function of r and not a function of beta. The phase, however, which is not a physical observable, could be a function of both r and beta. However, if it is a function of r, it will induce a radial component to the velocity because the velocity is proportional to the gradient of theta. If the velocity has a radial component, we will keep accumulating matter either on the edge or in the center, and that will not be a stationary solution. So we are looking for a stationary distribution of the matter in the superfluid. Therefore, theta can only be a function of the angle beta and not a function of r. For a stationary solution, the field should be unchanged after a full rotation. This periodic solution is fulfilled in the simple case where the phase theta is just equal to the angle beta. We could imagine other solution which will be also periodic. However, this is just the simplest one, and as usual we are driven by simplicity. So if we replace theta by beta in the expression for the velocity and taking into account the expression for the gradient in polar coordinates, so we get a velocity which is inversely proportional to r, which is at variance with what we had for the normal fluid, because in that case we had a velocity proportional to r. So the closer we are to the center, the faster the velocity is rotating. And this is diverging for r equal to 0, because then we have an infinite velocity. So we see that if we have a constant density and a velocity which goes to infinity for r goes to 0, then we have also a current which diverges. And to avoid this divergence of the current, the only possibility is for the density itself to go to 0 in the center of the superfluid. So we expect to find a hole in the center of the superfluid which is rotating, and when we move away from this hole, we will see a very fast rotating superfluid with an increasing density, and the further we go away from this hole, we will see a decreasing velocity and an increasing density. This behavior is called a vortex. These images have been obtained experimentally for systems of cold atoms. The atoms are trapped and cooled down using laser until we form a superfluid, and then another small laser is used to induce a rotation to the system. So the system is literally stirred. And what happened at first is nothing, because unlike a normal fluid, you can't rotate a small amount. And you can only excite a whole quantum of rotation or nothing. So this stirring is doing literally nothing, and then you slightly increase the speed until you reach this critical velocity, and bam, a vortex appears. So that little black dot we see in the middle of the superfluid is a hole corresponding to the center of the vortex. And that because you now have the ability to excite a whole quantum of rotation. So that's one vertex equal one quantum of rotation. And then you increase the velocity again, and you at some point have enough velocity to excite another quantum, and that's where two vertices appears, etc., until you get a third vertex, four vertices, 5, 6, 7, up to 13. So that was for the first experiment carried at the École Normale Supérieure in Paris, and soon after another experiment was repeated at MIT with many more vertices found in the superfluid.